Namaskar, I am Anand and you are watching Join for Education. Let's see the question answer, and these questions answers are from H.C. Verma. Let's see the first question. Listen the first question.
A charged particle moves with a velocity v near a wire carrying an electric current. A magnetic force, therefore, acts on it. If the same particle is seen from a frame moving with velocity v in the same direction, the charge will be found at rest. Will the magnetic force become zero in this frame? Will the magnetic yield become zero in this frame? Uns-
So this is the question. Let's see the answer. In this answer, we use the formula. The magnetic force is given by F Q V B sin theta, where F is the magnetic force, Q is electric charge, and this is equal to 1.6 into 10 to the power minus 19 coulomb. V is the velocity. Angle between magnetic force and velocity component. A charged particle is moving near a conducting wire, and also a frame is moving in the same direction which the charge is moving. Seeing from the frame, it is known that the charge is at rest, so velocity of the charge particles will be zero, thus magnetic force will be zero. When the charge is at rest, the current will be zero. We don't know either it is a positive or negative charge. Let us consider it is a negative charge. Seeing from the frame, negative charge is at rest, but there is a positive charge flow. Due to this, magnetic field will exist, so the magnetic field should not be zero. Let's see the question number 2. Can a charged particle be accelerated by a magnetic field? Can its speed be increased? So let's see the answer. For the answer of this question, we use the formula F equal to ma, where F is magnetic force, m is mass, a is acceleration. Here, the force, magnetic force which is acting on the charged particle, will try to accelerate it. If the charged particle is in the direction perpendicular to the magnetic field, then particle will move in a circular path. In that circular path, the direction of the charged particle will change. Formula used: magnetic force is given by F equal to QV B sin theta, where F is the magnetic force and Q is electric charge, and the value of Q is 1.6 into 10 to the power minus 19 coulomb. V is velocity, angle between magnetic force and velocity component. Force is always act perpendicular to the direction of velocity of a charged particle, so it cannot change the magnitude of the velocity of the charged particle. Velocity, magnetic field and force are perpendicular to each other, so it can change the direction of the velocity of the charged particle. So our answer is yes. A charged particle can be accelerated by a magnetic field, but its speed cannot be increased. It means that without increasing the speed of a moving charge, acceleration can be charged. So let's see the question number 3. This is the question number 3. Will a current loop placed in a magnetic field always experience a zero force? Will a current loop placed magnetic field always experience a zero force? Let's see the answer. Effect of the magnetic force on a current loop is totally based on uniformity of the magnetic field. Non-uniform, then current loop experience a force. So magnetic force on the loop will be zero. If the field is uniform, then the force experienced on the current loop either zero or non-zero. Let's see the question number 4. The free electrons in a conducting wire are in constant thermal motion. If such a wire carrying no current is placed in a magnetic field, is there a magnetic force on each free electron? Is there a magnetic force on the wire? Let's see the answer. Formula used. The magnetic force is given by F equal to I L B sin theta. Here I is the current, L is the length of the wire, B is the magnetic field, and if the electron is in motion, definitely there will be a magnetic force on it. Electrons are present in conducting wire, but current flowing in the wire is zero. When this wire is placed in a magnetic field, electron come to motion, but the motion will be random. So we can neglect the effect of force on each electron. So total magnetic force acting on the wire will be zero. Let's see the question number 5. This is the question number 5. Assume that the magnetic field is uniform in a cubical region and is zero outside. Can you project a charged particle from outside into the field so that the particle describes a complete circle in the field? Let's see the answer of this question. Magnetic field is uniform. Assumption: if the charged particle is perpendicular to the magnetic field, the particle will exhibit a circular trajectory. Let us consider that the charged particle is coming into the field from outside. along the positive y-axis, and let us take the field is in x-axis. X-axis is perpendicular to the y-axis, so magnetic field will be perpendicular to the charged particle. Then the particle will make a circular path. Let's see the question number 6. All of these are the theoretical question. ये सारे के सारे critical questions हैं. An electron beam projected along the positive x-axis deflects along the positive y-axis. If this deflection is caused by a magnetic field, what is the direction of the field? Can we conclude that the field is parallel to the z-axis? Let's see the answer of the question. If the force is acting in the y-axis, then the electron beam will be deflected from the positive x-axis along y-axis. The electron's motion is in positive x-axis, and then current will be along negative x-axis, and the force is acting along the y-axis according to the Fleming's left hand rule. The magnetic field will be in z-axis, so we can conclude that the field is parallel to the z-axis. Let's see the figure. This is the thumb magnetic field along the z-axis, current along the x-axis, and magnetic field along the y-axis. Here magnetic field along the z-axis, electron beam along the x-axis, and magnetic force along the y-axis. Let's see the question number 7. Is it possible for a current loop to stay without rotating in a uniform magnetic field? If yes, what should be the orientation of the loop? Answer will be yes. Formula used: the net torque of a loop is given by tau I AB sin theta, where tau is the torque, I is the current, A is area vector, B is the magnetic field, theta is the angle between area vector and magnetic field. When theta equal to 0, tau will be I A B sin 0, and the value of sin 0 is 0. Therefore, the value of tau or torque will be 0. When theta equal to 180 degree, the value of sin 180 degree is also 0. Therefore, the tau or torque will be 0. If theta is 0 or 180 degree, integral multiple of pi, then torque will be 0. So coil will stop its rotation. Theta equal to n pi represents that the magnetic field is in parallel with area vector, so the loop can stay in a uniform magnetic field without rotation. Let's see the question number 8. The net charge in a current carrying wire is 0. Then why does a magnetic field exert a force on it? Let's see the answer. Mostly positive charge on the wire is because of protons which are containing nucleus. When the protons are not in motion, the force acting on them will be 0. So charge will be 0. So charge will be 0, but there is a negative charge too. Negative charge is due to electrons. Here formula used Q V B sin theta, where F is the magnetic force, Q is electric charge, V is velocity, B is the magnetic field, theta is the angle between magnetic field and a charge. So when the electrons are in motion, the wire will carry current. Magnetic force will act on the wire. That is why magnetic field exert a force on the wire. Let's see the question number 9. The torque on a current loop is zero if the angle between the positive normal and magnetic field is either theta equal to 0 or theta equal to 180 degree, in which of the two orientations the equilibrium is stable. Let's see the answer of this question. Here used formula potential energy, which is generally denoted by capital U, equal to mb sin theta, where m is the magnetic moment, b is the magnetic field, and here theta equal to 0.1 Tesla, m equal to 7.85 into 10 to the power minus 11 ampere meter. If theta is 0, then the value will be cos 0 equal to 1, so the value will be minus 7.85 into 10 to the power minus 12 joule. If theta equal to 180 degree, then cos 180 degree, the value of cos 180 degree is minus 1. Therefore, the potential energy will be plus 7.85 into 10 to the power minus 12 joule. Of that, there is no problem to understand the answer of this question. If energy is minimum, then system will more stable. If energy is increased, then the system will lose its stability. For theta equal to 0, the energy is minimum and the equilibrium will stable for theta equal to 180 degree. Energy is maximum and equilibrium will unstable. Let's see the question number 10. Verify that the units Weber and volt second are the same. So let's see, formula used magnetic force FQVB, where F is the magnetic force, Q is electric charge, and value of Q is 1.6 into 10 to the power minus 19 coulomb. V is velocity, B is magnetic field, therefore magnetic field V equal to F by Q V. One of the unit that magnetic force measured in Weber per meter, Newton meter is Newton meter square. Weber per meter square equal to Newton meter square by coulomb per meter per second. ms is meter per second, c is the coulomb, v by m is the volt per meter. Weber equal to Newton per coulomb or volt per meter per second. We know that n by c equal to v by m. Weber v s 1 hour equal to 1 volt second. Thus the Weber and all the volt second are same. These are the objective questions. In the next class, I will answer these questions. Till then, thanks to all of you. Hope that this question answer will be useful to the schooling students, JEE, main and advanced aspirants to clear the concept of moving charges and magnetism, NEET aspirants and audience who are interested in physics. Once again, I thank to all of you. Thank you very much.